some practice that we're going to do with using the equilibrium constant, also known as KEQ. All right. So, question 1 first asks the question, well, given certain equilibrium constants, and we have 4 of them. Pardon me, I'm just going to adjust this camera. Which one favors products to the greatest extent? Which one favors the reactants to the greatest extent? All right. Well, first of all, we have, I guess we have 4 different KEQ expressions. Now, what's important is that KEQs, or equilibrium constants, range from 0 to infinity, and obviously they don't reach either of those, but values in between 0, 0 and 1, that's where our KEQ is dividing by a larger set of reactants. And values that are between 1 and infinity give a larger product over a smaller set of reactants. And the further along, the larger the number, the larger the products are relative to the reactants. In other words, the one that favors products greatest. So what we're going to do is we're going to go through and we're going to say, okay, question 1. So if KEQ is 2.2, so that tells me that the ratio of the concentration of the products over the concentration of the reactants is 2.2. So that tells me that when I divide these two numbers, I get the number 2-ish, a little bit bigger, which tells me that the products are about twice, or the concentration of the products, rather, is about twice as large as the concentration of the reactants. So this says the concentration of products is about 2.2 times as large as the concentration of the reactants. Okay, so this, therefore, the products are more heavily favored compared to the reactants. And so I could write that something like this. Writing something about twice as big. Yes. All right. So that wasn't quite what we're asked. We're asked which one favors products to the greatest extent. Okay, so we'll compare these. All right, so we'll look at our KEQ. That was KEQ1. So our KEQ2 is 1 times 10 to the negative 15. Okay, so that means when I divide the concentration of my products by the concentration of my reactants, I get the number 1 times, or rather really just 1 times 10 to the negative 15, really just 10 to the negative 15. Now it's important to recognize that is a number between 0 and 1, very close to 0. This is another way of saying 0.00000000000000000. 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And that's what this really says. So it's very small. So what that means is that our reactants are a much higher concentration than our products. That's how you get a number smaller than 1. You're dividing by a bigger number than your numerator. So this says the concentration of reactants is about, you know what, maybe I'll reverse that. Let's say the concentration of products is about 1 times 10 to the negative 15 of the concentration of the reactants. So it's a much smaller value than the reactants are. Okay, and so that tells us that, therefore, our reactants are most heavily favored. All right. So C has a KEQ. That's KEQ3 of 6.3 times 10 to the 4. Which it's important to recognize is a large number. It's 63,000. 1, 2, 3, 4. Yeah. So it's quite large. That says that we have a concentration of products. And when we divide that by the concentration of the reactants, we get a number that's quite large. Now, the way you get a large number through division is if the number on top, the numerator, is much bigger than the denominator. This tells us a ratio. How much bigger is this? Well, it's 63,000 times bigger. And so it says that the concentration of the products is 63,000 times greater than the concentration of the reactants. So, therefore, the products are the most heavily favored. Okay. And lastly, we'll look at question D. So D lists a KEQ of number 4, and it's 110. So what does that tell us? That tells us if we divide some number of products at equilibrium by the concentration of reactants at equilibrium, then we get the number 110. How do you get the number 110? If the products are 110 times bigger than the reactants. You can do this. You can pick any number that is 100 times bigger than another number. And when you divide them, you get 110. So let's do an example. I'm going to pick number 2200. And if I divide that, this is like a little aside here, by a number that's 110 times smaller than that, which I think is 22. Let's just check. Is it 110 times bigger? No, actually it wasn't. I didn't do that right. I guess it's 200. 220 divided by 200. I get number 11. Oh, it must be 20. Sorry. All right, so that means 200 divided by 20, and this number is 110 times bigger. So what does that tell us about the size of the products over the reactants? If you divide them and you get the number 110, that's 20, in case anyone's wondering. That means that we get a number of 110 as a ratio. Okay, so that means that the concentration of products is 110 times greater than the concentration of the reactants. Okay, so therefore, the products are more heavily favored. Now, the question actually asks, if we go back to the question, which of these 4 KEQs favors the products to the greatest extent? Which one favors reactants to the greatest extent? So I'm going to put these 4 KEQs, now that we've decided whether they favor the reactants or the products, on a number line, where it'll start at 0, go to infinity, and you can't have a KEQ of 0 unless, I guess, the reaction does not occur, in which case it wouldn't be in equilibrium, and it's going to go all the way to infinity. All right, so the first one we're going to list, I'm going to put as a borderline, the number 1 here. This is not going to be to scale. It's going to be somewhat logarithmic in scale. All right, so first thing I'm going to list the value of KEQ1, which is 2.2. So I'm going to put that here. And that's 2.2. All right, so it's bigger than 1 on our KEQ axis, our equilibrium constant axis. Our second option is 1 times 10 to the power of negative 15, so very small. So it's in between 0 and 1. It's very, very close to 0. So I'm going to exaggerate its distance from 0. And that's KEQ2. And that's 10 to the negative 15. Oops. Of course, that's 1 times 10 to the negative 15. All right, and then I've got KEQ3, which is 63,000, which is out here. And that's 63,000. And KEQ4 is in between. Which has a KEQ of 110. So as we see, like a logarithmic non-linear scale for this axis. All right, so we see that KEQ2 favors the reactants to the greatest extent. And KEQ3 favors the products to the greatest extent. And that's that question completed. All right, so let's move on. Let's look on to question number 2. All right, I'm just getting a piece of paper here. Let's do it on this weird off-white. All right, so for question 2, we're given a general function, a general reaction at equilibrium, and we can tell that it looks like energy is a reactant. It needs to go into this reaction in order for this to complete, which means we can see that this is exothermic, and this is endothermic. I just started writing it by accident, so I'm going to complete it. And this is exothermic going forward. Okay. Now, so what happens to the value of KEQ? What happens to the value of our equilibrium constant if the temperature is decreased? Okay. So what happens if you decrease the temperature? Well, this is an exothermic reaction. Oh, pardon me, it's I got that backwards. What a weirdo. Okay, it's exothermic going backwards. Sorry, and it's endothermic going forward. All right, now, if we are decreasing the temperature, Le Chatelier's principle says the reaction wants to go in the endothermic direction to release some extra heat from the bonds in these molecules. Okay, so I'll write that down first. If temperature is decreased, the reaction will shift in the exothermic direction. And that's Le Chatelier's principle. Okay. And so then it will therefore shift to the reactants. Okay, well, if you had a KEQ, an equilibrium expression, which is what we're asked about, and it gave us some value of the concentration of your products at equilibrium divided by the concentration of your reactants at equilibrium, And you perform this change, which means we shift to the reactant side, making more reactants. The reactants are going to increase in quantity, and the products are going to decrease in quantity. And how does a ratio change if the number on your top becomes smaller and the number on your bottom becomes larger? Well, let's compare it. Let's take some fraction. Let's say 3/5. Let's say 3/4. That's nice and easy to remember because that's 0.75, right? All right, so what if we make the number on the top smaller, say 2, and the number on the bottom bigger, say 10? What did that do to our fraction? Well, it became smaller. So that means as we shift to the reactants, we increase the amount of number we're dividing by, which decreases the value of our fraction. So, therefore, we would say KEQ will decrease. All right, let's see if we can use that reasoning to make it through question 3. So again, we've got another reaction, and we can see that this reaction is exothermic in the forward direction, and the backward direction is endothermic, because energy is a product that's produced by this reaction. All right. So what happens to this value of KEQ if our temperature is increased? So we're going to increase temperature here. So from Le Chatelier's principle states that if we increase in temperature, the reaction will shift in the endothermic direction. And therefore it will shift to the reactants. Again. Okay. Because the shifting to the reactants is endothermic. So what is that going to mean? Our original KEQ is going to have some concentration of products divided by some concentration of reactants. And as this equilibrium shifts to the right, the number of reactants is increasing. So our reactants are increasing in quantity and concentration, and our products are decreasing in quantity and concentration. So as a result, that means our KEQ will diminish or decrease. Same thing. All right. So let's move on. This question asks, question 4A. All right, so we're asked to explain how the reaction will shift. So which way will the reaction shift? And what will be the effect on our equilibrium constant if we increase the potassium ion concentration? So we're adding some potassium ions in aqueous form. And you know what, maybe it's better if I write the reaction. I'll just write it out over here. So we're mixing some potassium chloride, and this looks like it requires an input of energy in order to proceed. So maybe we're boiling it or adding heat. Maybe it's just sucking in heat from the environment because it's spontaneous. Who knows? We haven't really looked at the spontaneity yet. All right. So if I increase my potassium concentration, Le Chatelier's principle says we're going to want to undo that, so we're going to shift toward the reactants. So this means the reaction will shift to the reactants, increasing the concentration of the reactants. Okay, so that's part 1. But the question is now, what's that going to do to our equilibrium constant? What will be the effect on KEQ? Now, there's a very important thing here. This shift, if we are adding and changing concentrations, is only going to shift to restore the ratio of products to reactants. The only thing that can change our KEQ is a change in temperature. So KEQ will remain unchanged. So the ratio of reactants and products is still going to remain the same, even though we increased some of the products, and as such, we then increased some of the reactants as we shifted some toward the reactants. So those two shifts, or changes, I should say, cancel each other out, more or less, and they don't cancel each other out entirely. We do increase the concentration of both the reactants and products, but in tandem, which means that when we are dividing them, we end up getting the same value we did originally. So our KEQ remains unchanged. All right. For an increase in temperature, well, Le Chatelier's principle says that our reaction is going to shift to decrease amount of temperature, so it's going to shift in the endothermic reaction direction. So it's going to shift to the products. And so then the question is, okay, what's that going to do to the equilibrium constant? Well, if our equilibrium constant has some product concentration divided by some reactant concentration, and we are increasing the concentration of the products and we're decreasing the concentration of the reactants, that is going to mean we're going to be dividing by a bigger number on the top, and we're going to divide by a smaller number. How does that change a number? It has to change a fraction. KEQ increases as a result. All right, let's move on. So let's look at 4C. 4C, again, we're looking at the same reaction here. So the reaction says we're going to add more KCl, or potassium chloride, so we're going to increase KCl solid potassium chloride. And so Le Chatelier's principle says we're going to shift to the products. All right. And then the question is, okay, well, how does that affect KEQ? Again, you can only affect KEQ with a change in temperature, not with pressure, not with concentration changes. So KEQ remains unchanged. So just for the same argument as why adding potassium ions did not change the value of our equilibrium constant, adding more potassium chloride, well, reaction does shift to consume some of that and create a few more products. However, if our KEQ is a concentration of our products over our reactants, and our original change was to increase the amount of our reactants, our potassium chloride, we increased the amount of reactants, but then we diminished that a bit and added a bit more to the products, which is what a shift to the products does, then our KEQ will remain unchanged, provided we keep the temperature the same. All right, moving on. Something a little bit more formulaic. Okay, 5A. Write an equilibrium expression for the following reactions. All right, so this is pretty simple. We got to write the concentration of the products multiplied together, divided by the concentration of the reactants. And you might remember that if we have a coefficient of 2, that becomes a power of 2 in our equilibrium expression. Equilibrium constant expression, pardon me. All right, let's move on to question 5B. So again, all gases, so it means we're going to be including all terms. So our equilibrium constant is going to give a concentration of our nitrogen oxide or monoxide. And again, this coefficient of 2 is going to become an exponent. And then we have these two nitrogen gas components and oxygen gas. And they're multiplied together as reactants. All right. Next, we have this calcium carbonate reaction. It's a decomposition of calcium carbonate into calcium oxide and carbon dioxide. Okay, well, our reactants, well, we're not going to count our solid, so we're only going to write the concentration of carbon dioxide as a gas. And on our products, or pardon me, our reactant side, we only have the value of our calcium carbonate, which is solid, and so we're actually going to just write that in as a value of 1, meaning really the KEQ is just a concentration of carbon. That is a ratio of reactants to products. Pretty simple. All right, moving on to question D. All right, again, we've got to watch out for this liquid here. We are not going to be including the liquid in our equilibrium constant expression. All right, so we're going to start by our products, our HBRs. And we're going to square that because we have a coefficient of 2. And we're going to write only the hydrogen term. I should include the phases. It doesn't really matter if you include the phases. I would say most people don't. Don't worry about that, I would say. All right, and then lastly, okay, we have quite a big expression here, a lot of terms. We're just going to make sure, well, they're all gases, so they're all going to get included. We're going to list our products here. That's going to be raised to an exponent 6 multiplied by our nitrogen monoxide gas, which is raised to an exponent 4, divided by our ammonia raised to an exponent 4 times, this is all multiplied, times the concentration of our oxygen raised to an exponent 5. And that one I did skip including the phases. You could have included the phases if you like. All right, moving on. Okay, question 6. What would the equilibrium constant be for reaction 5A, this one, if at equilibrium the concentration of iodine chloride is 0.4 molar, concentration of iodine gas is 0.6 molar, concentration of chlorine gas is 0.1 molar. Okay, well, let's find out. So we're going to start out, we have a KEQ, of, well, we already wrote it out here, so it's our iodine concentration times our chlorine concentration, at equilibrium, of course, times our iodine chlorine concentration. We're a little dots there too, we can discriminate our iodines, and we're going to square those. Okay, so I'm going to write in my iodine concentration. What is my iodine concentration? My iodine concentration is 0.600 molar. I'm not going to include the units because I don't include the units in my answer right now, at least. That can be a pretty powerful analytic tool later, but for now, we're not going to worry about that. And then concentration of our iodine chloride is 0.4 molar, and we're going to square that sucker. All right, so I'm going to multiply those together. I get 0.0600 on the top, divided by 0.160 on the bottom when you square 400. And now I'm going to need a calculator, so I get 0.06 divided by 0.16, and I get a KEQ ratio 0.375, meaning reactants are reactants are favored over products, because this is a KEQ value that is smaller than 1. So we divided the products by the reactants. We got a number smaller than 1, meaning the number we divided by must have been bigger, meaning the reactants must have been bigger. Okay, moving on to question 7. So what would the value of the equilibrium constant be for question 5b if in a 1 liter vessel at equilibrium, contained these concentrations of nitrogen, oxygen, and nitrogen monoxide? Okay, so I'm going to steal my already worked out KEQ value for question B, or probably not the value, but the expression. And I can see here that it's my concentration of nitrogen monoxide squared over my concentration of nitrogen gas times my concentration of oxygen gas. All right, so what is the concentration of my nitrogen gas? Well, nitrogen contains 2 moles, or 0.2 moles, which is not a concentration. I have to divide that by the volume to get a concentration, and the concentration, or volume, is in liters. So this tells me that I have a concentration of 0.200 moles for every 1 liter. I'm going to square that value. Okay. I'll divide that by the concentration of nitrogen gas, which again is 0.420 moles, but not a concentration yet until I divide it by liters. Now, it just so happens in this case that divided by 1 is not going to change our values, which is nice. But as a stepping stone, we'll see in the next question, it will be important that we include or make sure we're converting between moles and molarity. And lastly, what do we have? The concentration of oxygen, 0.931 moles for every 1 liter, which is to say we have a 0.200 molar solution squared divided by a 0.420 molar solution times 0.931 molar solution. Now, we don't actually need those units, but we need to make sure they are concentration units before we go forward. So that's all I'm illustrating here. We're going to forget those units in a second. That is an M, by the way. All right, so what do we got? 0.2 to the power of 2 on the top. We're going to divide that by 0.42 and divide that by 0.931. So we get a KEQ value, which is 0.102, which again suggests that the reactants are favored over the products. Okay, lastly, move on to question 8. Question 8 asks us for the value of the equilibrium constant in reaction 5E. 5E. If a 3-liter vessel at equilibrium contains 0.80 moles, 1.80 moles of ammonia, 2.40 moles of oxygen, 0.600 moles of water in vapor form, and 4.5 moles of nitrogen monoxide. All right, so again, I'm going to steal from question 5E my equilibrium expression. And that's going to say that my concentration of water is raised to an exponent of 6. My concentration of nitrogen monoxide is raised to an exponent of 4. My concentration of ammonia has an exponent of 4, and concentration of oxygen has an exponent of 5. Okay, what's my concentration of water? We'll start there. Well, I know I have 0.600 moles, but I'm also in a 3-liter vessel. So my concentration of water is 0.600 moles over 3 liters. And that's all raised to the power of 6. This is going to be an interesting number. All right, and my ammonia, pardon me, not my ammonia, my nitrogen monoxide concentration. So I've got 4.50 moles, all divided by 3 liters, as raised to exponent 4. And my ammonia concentration is going to be 1.80 moles over 3 liters. And that's all raised to an exponent of 4. And I've got 4.5 moles of nitrogen. Wait, no, sorry. Sloppy. 2.40 moles over 3 liters. And that's raised to power 5. All right, great. You know, just because I'm kind of interested to see how this all turns out, I'm actually going to try and do some of this by myself. So I'm going to say that's going to give me a value of 0.2 molar raised to an exponent of 6. That's times 1.5 molar value raised to an exponent of 4. I'm just sort of curious to know how this stuff all sort of balances out, and if it ends up being doable without using a calculator. You can just skip maybe a minute ahead if you're interested in just knowing what the answer is when you punch into a calculator. But, I mean, I gotta entertain myself somehow during these videos. And I kind of like stuff like this. So what do I got? 2.4 over 3, that's going to be 0.8. 0, 0. I should only include 2 zeros, actually, if I'm talking about sig figs. All right, now I'm interested. I feel like these are going to balance out some way. All right. Maybe they don't. All right, well, let's just see. So I'm going to say that's 0.200 molar times 1.5 molar. That's all raised to the power 4. And then I've got 0.200 times 2. And so and then I've got 0.6 times 0.8. Okay, I can see this isn't going to work out so super nicely, I don't think. So I'm just going to start punching it in. So we've got 0.2 raised to an exponent 6 times 1.5 raised to an exponent 4. That's some fraction, some long decimal, and then I'm going to divide it by, I'm going to open a set of brackets to make sure I don't miss anything, 0.6 raised to an exponent 4 times 0.8 raised to an exponent 5. Okay, yeah, and it just becomes some ugly thing. Actually, I wonder if that is a nice fraction. I'm just going to test it. It's 125 over 16,384. Okay, so it wasn't going to simplify that well after all. All right, so anyway, my KEQ value is 0.00763, which again suggests that my products, so my reactants, are favored by a factor of roughly 1,000, close to 100. So reactants are much more heavily favored over the reactants. All right, and that's it. That's how we go through these questions. So let me know if you have any questions about any of that, and maybe we can talk during Flex Block or after school sometime.